Good morning. So this is going to be our unit 15, our last unit, and it is going to be over uh, nuclear chemistry. As a little bit of review, let's go back and look at these sorts of symbols. And so when you have the chemical symbol as X, and then we have a number in front but up top, and a number in front and down at the bottom. And so that Z number represents the atomic number, which is the number of protons. And then that A number up there, that represents the mass number, which is the number of protons plus the number of neutrons. And then not shown there, but referring back to atoms, is the atomic mass, which is the number listed on the periodic table. And that's all kind of weird and decimally because it is a weighted average of all of the naturally occurring isotopes. And then that would sort of raise the question, what are isotopes? And so let's review that. Isotopes are atoms that have the same number of protons, and because they have the same number of protons, they are technically the same element, and so they would have the same chemical symbol, but they have different numbers of neutrons. And because they have different numbers of neutrons, that would mean they have different mass numbers. Isotopes are often confused with ions, and so let's review. Ions are atoms that have gained or lost electrons and therefore carry an electrical charge. So let's try to not get those confused. Isotopes have different numbers of neutrons, and ions have different numbers of electrons than they should. Ooh, all right. And when we refer to particular isotopes, we use their mass number as an identifier. So when we refer to something as carbon-14 or uranium-235 or potassium-40, those numbers, the 40, the 235, the 14, are referring to the mass number. All right, how nuclear reactions differ from chemical reactions? Well, chemical reactions only involve electrons and the rearrangement of electrons between atoms. So chemical reactions are driven by the rearrangement of electrons. They can transfer, they can share, they can be sharing and then go share with something else. Bonds can break and new bonds can form. So that's all chemical reactions are driven by. And nuclear, as the name would suggest, are driven by changes in the nucleus of an atom. So nuclear reactions involve the rearrangement of the particles within the nucleus. Nuclear reactions are much more energetic than chemical reactions. So nuclear reactions yield exponentially more energy than chemical reactions. As an example of that, so a nuclear power plant can yield as much electricity as a traditional power plant. So, one handful of uranium, well, you wouldn't want to hold it in your hand because it would like burn clean down to the bone. But so one handful of uranium can generate the same amount of electricity as carloads and carloads, not passenger cars, train cars full of coal. And so that difference comes from the fact that mass is often converted to energy in nuclear processes, mass is often converted to energy. That is governed by the equation E equals mc squared. And remember that C was a number, it's 3.0 times 10 to the 8th meters per second. And so that 3.0 times 10 to the 8th then gets squared. And so a small amount of mass converted to energy yields a tremendous amount of energy. All right, so what makes a nucleus stable? Well, nuclear stability depends on the ratio of protons and neutrons. See, protons that are separated by just a little bit are going to repel one another with electrical force. But two protons that are actually in contact with one another will exert an attractive force on one another. So, if protons are separated by a little bit, they're repelling. If they're actually in physical contact, they will hold on to one another. Neutrons are there, they will exert an attractive force on anything they touch. Other neutrons, the protons, so the neutrons are there to exert an attractive force on all the particles it is in contact with. So the neutrons are there to hold the nucleus together. But if the ratio of protons and neutrons is such that you can't have it stable, then you have an unstable nucleus. So here's a graphic to represent that. So you have neutrons there, they are attracting each other. They are also attracting the protons together, and so this whole thing has this attractive force. And in a small nucleus like this, you have two protons that aren't touching, and they are repelling one another, and so, you have a little bit of repelling force, but a whole lot of attractive force. So this would be a very stable nucleus. The greater the number of protons, the greater the number of neutrons have to be, because the more protons you have, the more they are going to repel one another, and the more they repel one another, the more you're going to need the neutrons to hold all of that together and try to make it stable. But once you hit a certain number of protons, no amount of neutrons are going to hold it together. So every element above number 83, that's bismuth, has too many protons, and every isotope of that is going to be in some way, shape, or form radioactive. Now, there are radioactive isotopes before number 83, but 83, above that, you can't have a stable nucleus. And so let's talk about what does it mean to be radioactive. So what does it mean to be radioactive? It means that in order to achieve stability, the unstable nucleus will eject certain particles. And so you kick out the particles, and then you are going to have a good proton-neutron ratio, which can lead to a stable nucleus. These particles are very energetic, and so when we hear radiation, we think bad and dangerous, and that is sometimes the case. But these particles that are ejected from the nucleus are going to be very energetic, and when those very energetic particles collide with biological material, they can just, sometimes they can cause mutations, but they can also just punch holes right through that biological material, and then if enough cells are damaged, it's going to kill the organism, which is, very bad in some ways, but we can also use it, most fruits are exposed to low-level gamma rays, and it kills any little pests on there so that, they have a longer shelf life. So, it can be used for good and evil. The types of radioactivity. Do not write down this slide, because we're going to go and talk about each of these types of radioactivity individually. So if you write this down, then you're not going to leave enough room, and then you're going to regret it. So this is just an introduction. The types of radioactivity. You can have alpha particle emission, beta particle emission, gamma ray emission. Sometimes it's called gamma particles, but it's not really a particle, so that's silly. And then you can have positron emission. So the first one we'll talk about are alpha particles. And so alpha particles, they consist of 2 protons and 2 neutrons, which means you could write them as, because it's going to have a mass number of 4 and an atomic number of 2, so you can write an alpha particle, so that's the Greek letter lowercase alpha, and then mass number 4, atomic number 2, and these guys are actually, once they slow down, so when they come out of the nucleus, they're traveling really fast and they're going to tear through things, but once they slow down, they'll become a helium atom. And actually, all the helium that we have on Earth comes from alpha decay of radioactive nuclei. So those are alpha particles. So let's write the equation for the alpha decay of astatine-210 and osmium-188. So we'll give you a couple seconds and you can try that out. All right, so astatine-210 and osmium-188, and if they're going to decay by alpha particle emission, so that means they're going to kick out an alpha particle. And so the way that you're going to do this is the mass numbers and atomic numbers cannot change. So it helps to actually write down the atomic numbers of everything, including the mass numbers too. So like on alpha, you can go 4, 2, 4, 2, and then astatine, AT, so that's number 85, and osmium is number 76. And so they're going to eject alpha particles, but then there's going to be an atom left over that is hopefully more stable than the radioactive isotope. And so the alpha particle, so it's going to be something with 4 adds up to 210, so that's going to be 206. And then something with 2 adds up to 85, so that's going to be 83. And then I got to go to the periodic table and find what is element number 83, and oh, it's bismuth. All right, and then osmium 188 decaying into an alpha particle, and so it would be 184 and 74, and the mass numbers and atomic numbers all add up to equal osmium, and number 74 on the periodic table is tungsten. All right, next we have beta particles. Beta particles are produced when a neutron becomes a proton. It all has to do with quark interactions inside of the nucleus. Okay, so just believe me, a neutron becomes a proton. And Google it, and I'm sure you can find a cool YouTube video. Minute Physics has one, but for now, just go with it. A neutron becomes a proton. And so a beta particle will have no mass because proton and neutron have the same mass, but it will have a charge. So it has an atomic number of -1. And so it can be written as 0, -1, and then that is the lowercase Greek letter beta. So it looks kind of like just a fancy curvy B. And then once it slows down, it's actually behaves as an electron. So, you know, once it slows down. So comparatively, alpha particles are bigger and bulkier and have more of a charge, so they're easier to stop. They carry more of a wallop, though, so the thing they do hit will get hit hard, but then they'll come to a stop. Beta particles can travel through things further, but since they are smaller, they have no mass, but they're still charged. They can carry a wallop, but they can travel further into material. So like an alpha particle will barely penetrate your skin, but a beta particle can, make it through most of your skin and then into the tissue beneath it. So let's look, we'll go to the next slide. So write the equation for beta decay for sodium-24 and for strontium-88. And it'll be real similar to the way that you did that alpha decay stuff. So give this a whirl, and then we can see what the answer is. So we have sodium-24 and strontium-88, and they are going to decay by beta particle emission. And so sodium ejects a beta particle, and the numbers on a beta are 0, -1, and so we'll just write those on in there. And sodium is number 11, and so the mass number of the leftover atom is 24, and the atomic number would be 12. I go to the periodic table to find out what number 12 is, and it is magnesium. Then strontium. Strontium is atomic number 38. And so the leftover atom here is going to be number 39, which is yttrium. So 39, and the mass number would be the same, it'd be 88. Yttrium. All right, next we're going to talk about gamma particles, but really gamma rays, because gamma, it can be written like this, so it's kind of like a curvy, fancy Y. It's the lowercase Greek letter gamma, but it is, look, it's 0 and 0, no charge, no mass. So gammas are actually pure energy. So they are like very, very energetic light. And so X-rays, we are familiar with those. They're super energetic light. Gamma rays are the next down the spectrum. They are the most energetic form of photons. And so if you think about it as a photon, it's a particle, but really more times than not, gammas we talk about as rays. And so since they are not a particle per se, they come about from the settling of the protons and neutrons into a more stable configuration. So nothing is ejected from the nucleus other than energy. And so where did the energy come from? It came from a high energy situation in the nucleus settling into a lower energy situation. And since gamma rays, they usually accompany another type of radioactive decay, because after you kick out a beta particle, well, now you have an extra proton. That proton shifts around inside of the nucleus, finding a more stable configuration, and then that releases, that going from high energy to low energy, releases the gamma ray outward from the nucleus. So these are actually really easy. When you go through gamma ray emission, you have the exact same atom as you did before. Next, we're going to talk about positrons. So positrons come about when a proton becomes a neutron, very similar to beta decay. So similar, in fact. So betas positrons are just the evil twin brother of betas. And so a positron has no mass and an atomic number of +1. You can write it as the same symbol, beta, but with a positive symbol up there. And then it would be a 0, +1 for its number values. Oh, sorry, that was pretty fast, so we can pause it if you need to write some stuff down. And then let's try writing the equation for the positron decay of potassium-40 and sulfur-31. So give that a try. So we have potassium-40 and sulfur-31, and they are going to decay by positron emission. And so the number on a positron is 0 and +1. Potassium is number 19. And after a potassium 40 decays, it is going to yield an argon 40 atom. And then we have sulfur, sulfur 31. Sulfur is number 16, and so when that decays by positron... That was fun. You're just gonna... Class is not over. Alright, so when that decays by positron emission, it's 0 + 1, and then the leftover atom is going to also be 31, and it would be number 15, which is phosphorus. The rate of nuclear decay is very steady, so isotopes decay at a very particular rate. Now, that doesn't mean that they're common, so there are isotopes that have so let's talk about how we measure the decay rate. So scientists use half-life to convey the rate of nuclear decay, and the half-life is equal to the amount of time required for half of a radioactive sample to break down. And half-lives, so there are isotopes that have a half-life of half of a second, and there are isotopes that have a half-life of 2 billion years, and it can range from anywhere in between. But for a particular isotope, the half-life is always the same. And so then we have some questions regarding half-life. And so if you can count and divide by 2, these problems should be pretty straightforward. So if I start with 96 grams of francium-223, how much of the sample will remain after 4 half-lives pass by? So think about that. So it's going to get cut in half once, twice, 3 times, 4 times. So we'll pause and take a second, try and answer it. And The answer, 6 grams. So 6 grams would be left after 4 half-lives go by. All right, next question. After 24 hours, only 3 grams of holmium-163 remain of an original sample with a mass of 192 grams. What is the half-life of holmium-163? So the amount of time that's gone by is 24 hours, and it was reduced from 192 to 3 grams. So we need to try and figure out how many half-lives have gone by in order to go from 192 down to 3 grams, and then take into consideration that that many half-lives took place in 24 hours. So try and work through that one. This is a little trickier one, but try and work through it. We'll pause and then look at the answer. All right, so the answer is 4 hours, because to go from 192 down to 3 grams, it would take 6 half-lives. 6 half-lives in 24 hours, that means each half-life was 4 hours. Next question is, the half-life of gallium-68 is 42 hours. How much of a 100-gram sample will remain after exactly 1 week? So we need to figure out how many hours are in a week, how many half-lives will pass by, and what that would mean for the 100-gram sample. So take a second, we'll pause, work through it, and then we'll check the answer. All right, and I got 6.25 grams because 42 hours would pass by 4 times, and so it would get cut in half 4 times, and so that would leave us with 6.25 grams. All right, and then the last things we need to look at are nuclear processes. So how do we use, how are nuclear processes used in our lives? And so fusion is the first one we'll look at. Fusion is the combining of smaller nuclei into larger nuclei, and there will be an accompanying release of energy. And fuse, right? So fusion, fusing is like putting things together. So that's, how you can kind of hold that in your brain. And this process takes place inside of stars. So this is the process that fuels the stars. And that's why they can yield so much energy, because they're converting mass to energy inside of their core. Well, is it in the inside or that? I don't know. It happens inside of stars. I don't know my star anatomy. The other process that we'll look at is the opposite of fusion. It is fission. So fission is the breaking apart of large nuclei into smaller nuclei with an accompanying release of energy. Fission, this is what powers atomic weapons and nuclear power reactors. So the nuclear power plant on or nuclear engine on a submarine, or the nuclear power plant down in Callaway, or the atomic weapons that were used at the end of World War II. All of these took advantage of fission. And so if you're skeptical at all like me, well, I just said that you can get energy out of joining together small nuclei into larger nuclei, and now I'm saying that if you break large nuclei up into smaller nuclei, you can get energy. Well, it sounds like you can just get energy from whatever process, and that's not actually the case. So anything smaller than iron can be assembled to get energy out. Anything larger than iron can be broken down to get energy out. But iron is that dividing line. So iron is the dividing line between being able to get energy out of fusion or energy out of fission. So if I want to build up a heavier atom, well, then I have to put in more energy than I would get out. And if I want to break apart a smaller atom, I would put in more energy than I would get out. So iron is that dividing line. And then we have this nice graphic here that sort of illustrates it. So inside of the sun, you have hydrogens getting fused together, and then ultimately they will yield a helium atom, and you get a whole bunch of energy out of that. And then you have fission and uranium-235. That's what's used in most nuclear weapons or power plants. And so then when that breaks down, it releases these different atoms and a whole bunch of energy and some free neutrons. And then there's this graphic as well. It just sort of sums up the whole nuclear or radioactive decay. So you have the nuclear force trying to hold a nucleus together, but you have electrical repulsion, which is trying to push it apart. And in order to achieve stability, you can kick out an alpha or a beta or a gamma. And, I couldn't find one that had positrons on there too. So, but positrons could also be kicked out. So there you go. There's the nuclear unit. Work on your homework, be cool to the sub, and look over your acids and bases tests. And I should be up at some point, and we can talk some stuff through.